A couple of units of study ago, we investigated the circuits that are made by connecting multiple capacitors together, either in series, in parallel, or in combination. And then so far in this unit of study, we've been investigating the same sort of circuits made with combinations of resistors. Sometimes those circuits are reducible into one single equivalent resistance. Sometimes we have to apply Kirchhoff's junction rule and loop rule in order to find how much current flows in each part of a circuit. Well, here's a different situation. Now we have a capacitor and a resistor connected together with some ideal voltage, and I've included a switch on this circuit. So before we close the switch, let's say this capacitor initially is neutral. When we drop the switch, if that resistor wasn't there in the circuit, then the capacitor would charge up almost instantaneously. I say almost because even the wires that are used to make the connection between the battery and the capacitor have some non-zero resistance, maybe negligible, but still not zero. And so it limits the rate at which current can flow and conduct electricity off of the top plate and conduct electrons onto the bottom plate of the capacitor. That's exactly what happens, right? So which way will conventional current flow in this circuit when the switch is closed? In the direction that you're supposing, in a clockwise direction. However, it's fair to say that there's some current flowing to the left through this resistor, and that same amount of current flows through the battery and flows through the switch, but that current doesn't flow through the capacitor because remember, the capacitor has a insulating gap, right? There's some dielectric material that doesn't conduct electricity at all. So we should talk about what's really being conducted here. As soon as we drop the switch, the battery places a potential difference across the ends of the wire, and it establishes an electric field within the wire, and electrons, the electrons here and some of the electrons that are on this plate of the capacitor, all these electrons begin to drift counterclockwise in this circuit loop, right? In the resistor, they're drifting in this way. And then in the end, they're going to end up being deposited on this bottom plate of the capacitor. So in time, the bottom plate becomes negative. Whatever electrons have been conducted through the circuit have ultimately come from this top plate, so it becomes positive. And there you have it. There's no current through the capacitor, but there's current through the resistor, the switch, and the battery. Well, it's going to take some time for this process to take place for the capacitor to become fully charged, because the current can only be so great based on the amount of resistance, right? Ohm's law tells us that the amount of current is equal to voltage divided by resistance. However, the voltage across the resistor is not constant. So what we want to come up with is an equation for how the current in the circuit is a function of time. So notice I'm using lowercase I for current now. If it's a steady value, I might use a capital I as a way to signify that it's a constant singular value, but because the current varies with time, then I'll use lowercase I to indicate that current is a variable. So let's see, I want to apply Kirchhoff's loop rule to this circuit. I want to start here at point P, and then I'm not saying necessarily that current is flowing this direction. I just say I'm going to trace my way around the circuit like this. Actually, I'm pretty convinced that the current is going to go in a clockwise direction. Now, that current doesn't go through the capacitor, but that clockwise symbol right here for current lets me know that current flows to the left through this resistor, and I need to know that in order to determine the polarity of that resistor, right? When I apply Kirchhoff's loop rule, I said the first thing I encounter is positive EMF because I'm going from the negative to the positive terminal. There's no voltage gain or lost across a switch. Okay, and then I go across this capacitor. Now, I'm going from the positive terminal to the negative terminal as I trace my way around this circuit in order to determine changes in electric potential. So this is going to be minus the voltage across the capacitor. Then we go this way across the resistor. I'm going in the direction of the current. So again, that's a voltage loss. So minus the voltage across the resistor, and I'm back to point P. That equals 0. So how do we calculate voltage across a capacitor? Let me remind you here. Q, V, C. So voltage is charge divided by capacitance. I actually should replace this with a lowercase q, because again, the amount of charge on the plates of the capacitor, that starts out at 0, right? At time t equals 0, the charge on this upper plate is 0. It takes time for electrons to be conducted off that plate. Eventually, the potential difference reaches the potential difference provided by the battery, and then the current reaches 0, charge stops growing on the plates, and we reach the steady state value. Okay, how do we calculate voltage across a resistor? That follows from Ohm's law. So voltage is current times resistance. So I can take this equation and rewrite it as EMF minus Q over C minus IR is equal to 0. I can turn this into a differential equation by noting that current is the rate of change of charges, the flow rate of charge, right? So now we get EMF minus Q over C minus R times dQ dt is equal to 0. Let me multiply it all the way through by capacitance. So we get capacitance times battery voltage minus charge minus the product of resistance and capacitance times dq dt is equal to 0. Now we're trying to come up with, we're trying to come up with two equations. One, what's the charge on the capacitor as some function of time? And if we take the first derivative of that, then we can get the current in the circuit as some function of time. So let's make this our number one objective, and then it'll be straightforward from there to satisfy this number two objective. So yeah, keep in mind that this Q here represents some function of time. So I have a differential equation. I've got a constant, and then I'm subtracting this quantity that's a function of time, and then I'm also subtracting some constants multiplied by the first derivative of that function with respect to time. So isolating for Q is a little bit of a challenge, but not too complicated, the math we have to carry on here. So let's see what we get. Let's separate out variables, right? Q is a variable, it's a function of time, and of course time is a variable. So we want to try to get Q on one side of the equation and T on the other side of the equation. So how about negative RC dQ dt is equal to Q minus capacitance times EMF. So I've just transferred some of the terms in the equation to other sides of the equation. Looks good, looks good. Step 6, some cross multiplying, and we get dQ over Q minus capacitance times EMF is equal to negative 1 over RC times dt. So at this point, we can take the integral of both sides of the equation, because now all we have is one variable on the left and one variable on the right, and so we can do calculus of a single variable on both sides of this equation. Oh, I should consider my limits here. So remember, time t equals 0 represents the moment that I drop the switch, and at that point the charge started at 0. At some time later, there's going to be a charge of Q on these plates. So as the time goes from 0 up to some random time t, the charge goes from 0 up to some random charge q. And I think you recognize the solution to the integral expressed on the left side of the equation would be natural log of q minus c e, and I have to evaluate that from 0 to q. On the right side, I can pull negative 1 over rc out of the integral, and then I'm just left taking the integral of dt from 0 to t, which is going to give me t. We've got a few more steps, and we'll get to the outcome we're looking for, so hang in there. Let's see, this is going to be the natural log of q minus c epsilon minus the natural log of negative c epsilon, and that equals negative 1 over rc times t. I guess a better way to say this is the natural log of q minus c epsilon over negative c epsilon. Whatever I do to one side of the equation, I'll do to the other. So e raised to whatever expression is represented on both sides of the equation. That causes the natural log to cancel out. We have q minus c epsilon over negative c epsilon is equal to e to the negative t over rc. And then lastly, with a little cross multiplying and transferring terms from one side of the equation to the other, we have q is equal to c times epsilon times 1 minus e to the negative t over rc. Let's think about this. What's a graph of charge versus time going to look like? We know it starts out at 0. Let's make sure that's right. E to the negative 0, to the negative 0, that's e to the, anything to the 0 power is 1, right? So when t equals 0, we have 1 minus 1. Oops. Yeah, sure, when t equals 0, the charge is 0. So what about, well, let's just fast forward to some really large amount of time. Let's just pick a time way down the time axis here. So we're going to have 1 minus e to the negative some really large value. That's the same thing as 1 minus 1 over e to some really large value, which is the same as 1 minus some very small value, which if it's small enough we can disregard, and so we just get 1. And so it seems like the charge is approaching the product of the capacitance and the voltage. Well, of course. Charge is voltage times capacitance. Here we're using the symbol for ideal voltage, and we're saying q is lowercase q because it's a variable, right? So it looks like we have an asymptote, right? The maximum value of charge we can get is the product of capacitance and battery voltage, and it's going to take a long time to get there. So that's the graph of charge versus time. So we've got it. Charge is a function of time as described by the equation q equals ce times 1 minus e to the negative t over rc. R times c. I'm curious about that product. Let's see, we've got ohms multiplied by farads. I'm going to let Ohm's law guide my thinking of what an ohm is in terms of other variables. See, V equals IR. Resistance is volts per amp. So let me call this, instead of an ohm, let me call it a volt per amp. And instead of a farad, let me call that a coulomb per volt. In that way, volts cancel out. Now I'm left with coulombs per amp. Let's see, a coulomb per amp. I don't want to call it an amp. I want to call an amp a coulomb per second. Oh, yeah, so we end up with, oh, this is seconds. Ohms multiplied by farads is seconds. Well, it has to be, right? I can't raise the base of the natural logarithm to some numerical quantity that has units. I can only raise it to just a strict numerical value. So if the numerator is time, then the denominator has to have time units. So what time value is the product of R and C? Well, let's see. What if we let t equal 0? Well, we already found that, and this just becomes e to the 0, which is 1. And 1 minus 1 gives us 0, and so q would equal 0. Here we can make a chart. When t equals 0, q equals 0. And then we already found out as t approaches infinity, q approaches the product of capacitance and voltage. So here's a time to consider. What if the time is the product of the resistance and the capacitance? Then we get e to the negative RC over RC, or in other words, e to the negative 1, or in other words, 1 over e. So the charge would be equal to capacitance times voltage times 1 minus 1 over e. And you should remember that the base of the natural logarithm is 2.718. So what do we get when we calculate 1 minus 1 over 2.718? You can try that on your calculator yourself, see what you get. You get 0.63. In other words, we can say when the time is the product of R and C, the charge is equal to 63% of the product of capacitance and EMF. Now we might as well just call that capital Q, the maximum amount of charge we can develop on the plates. In fact, we give a name to this product of R and C. We say that's a special amount of time we call the time constant, and we represent it with a capital Greek letter tau. So this time constant doesn't represent the time it takes for the capacitor to fully charge, because after all, that takes an infinite amount of time. The time constant tau represents the time it takes to reach 63% of the maximum charge. If we go back to our graph of charge versus time, let's see, if this is all 100%, then 63% would be about there. So if we read across and read down, then this value on our time axis would represent tau, the product of the resistance and the capacitance, the time that gives us an amount of charge equal to 63% of the maximum charge that's going to develop on the plates. So what's current as a function of time? Well, charge as a function of time is maximum charge times 1 minus e to the negative t over tau. And the current is the derivative of that expression with respect to time, which gives us q minus qe to the negative t over tau, right, d dt of all that. Of course, the derivative with respect to time of this constant gives us 0, so we really only need to take the derivative of this part of the expression. So I is equal to, let's see, negative 1 over tau times negative q times e to the negative t over tau. These negatives cancel out. And remember that tau is the product of R and C, and Q is the product of capacitance and battery voltage. So this C cancels out, And no surprise, we get I is equal to voltage divided by resistance. That's just Ohm's law. And then multiplied times e to the negative t over tau. Let's make a chart. Time and current. So when the time is 0, then we've got e to the 0, which is just 1. And so 1 times voltage over resistance. There we go. And let's fast forward. Let's let t approach an infinite value. Then we've got battery voltage divided by resistance times e to the negative infinite, which is the same thing as 1 over e to an infinite value, which is basically 0. And if the time is the time constant, then we have e to the negative tau over tau, which is e to the negative 1, which is 1 over 2.718, which is 0.37. So we get 37%. Of course, we could replace this and say I is equal to I maximum times e to the negative t over tau. So then we can just call this I maximum, and we can call this 37% of I maximum. Let's make the graph. Current versus time. At time t equals 0, starts out at its maximum value. And what is that maximum value? It's the battery voltage divided by the resistance in the circuit. And from there, it asymptotically shrinks towards 0. It takes an infinite amount of time to get to 0, but it doesn't take an infinite amount of time to reach 37%. If this is 100% of the maximum current, then this maybe represents 37%. So if we read across and then read down, you guessed it, this value is tau, the product of R and C. So we can think of this quantity tau, the time constant of an RC circuit, as being either the time it takes for the charge to reach 63% of the maximum charge, or we can think of it as the time it takes the current to reach 37%, or to not reach, to drop down to 37% of its initial value we call I maximum. And by the way, this Q max happens to equal the product of capacitance and voltage, and this maximum current is equal to the voltage divided by the resistance. Whew, that was a lot to take in. I encourage you to revisit the notes you took off of this lecture video, and in fact see if you can derive this equation and this equation on your own, starting from an analysis of this circuit diagram, in particular applying Kirchhoff's loop rule as your starting point.